Good morning guys and welcome to Mind Your Math. In today's class we are going to learn about irrational numbers. So we will be continuing from the fundamental theorem of arithmetic and we will be moving down to certain theorems regarding irrational numbers. Now this part of this chapter real numbers, it is pretty much easy because there are only a few questions that can come from this particular part. So now if you have any doubt regarding the concept that I am covering in this particular video, you can mail me in the mail ID given below in the description box. So in grade 9, you have already learned the basic definition of irrational numbers. So when I am talking about irrational numbers, you immediately relate it to rational numbers. So what is a rational number? A rational number is any number that can be represented in the form of P by Q, where P and Q are integers and Q cannot be 0, which means the denominator cannot be 0. So any number which is not rational is an irrational number. So an irrational number cannot be represented in the form of P by Q, where P and Q are integers. Now, in our college, in our school days, so till now, we have learned about so many number systems. We have learned about natural numbers, then we added a 0 and we called it whole numbers. Then we learned about integers by putting in negative signs. Then we learned about fractions. We learned about rational numbers and we learned about irrational numbers. We are going to learn a new theorem regarding irrational numbers, and using that particular theorem, we are going to do a few sums in which proving is required. So basically in this particular part, only proving sums we are doing. So sums like prove that root 2 is irrational, root 3 is irrational, etc. So now let us start with what are irrational numbers. We already saw the definition. So a few examples of irrational numbers would be root 2, root 3, pi, etc. Now we know that whenever there is a prime number p under a square root, it automatically becomes an irrational number. So in general, I can say that root of p, where p is a prime number, is an irrational number. Right? Okay guys, if p is a prime factor of n, p can divide n without leaving a remainder. Correct? You don't have any doubt in it. If you have a number 36 and 3 is a factor, you know that 3 can divide 36 without leaving any remainder. If n can be represented as the product of primes, fundamental theorem of arithmetic, one of the factors will be p. Because I have already mentioned p is a prime factor, and p1, p2, p3 up to pn can be the same prime factor or a different prime factor, but this is the only way in which n can be represented. You cannot bring in any additional prime factor than what is there in the factorization of p, factorization of n. Okay, suppose I have a number a. Okay, I am representing the prime factorization of a as p1 into p2 into up to pn, where all these are prime numbers. So basically the fundamental theorem of arithmetic, a can be uniquely expressed as a product of primes. Okay, my friend comes in and says that I have a factor p which is a prime factor, and I know that this number p properly divides a. So I say that yeah, I know it is true. So in that case, p has to be equal to one of these values. P should be either equal to p1 or equal to p2 or equal to p3, because p is properly dividing a and p is a prime number, so it has to appear in the prime factorization. Correct. Now I decide to multiply this number a with one more a. So what happens to the prime factors? Each of the prime factor becomes double. Not double, it becomes a square. Correct. So now my a square becomes p1 square into p2 square up to pn square. Okay. Now what can I say about the factor p? I can say that this factor p will divide a, as well as this factor p will be there in a square also, because p was already a prime factor of a and a square happened by multiplying a with a. Basic? So far so clear? Now let us move on to the theorem. Let p be a prime number if p divides a square, p divides a, where a is a positive integer. So this is our theorem. Now it is mentioned in the textbook that this is not from the examination point of view. This is just the basis for proving why root 2 is irrational or root 3 is irrational. So Understand the theorem properly before you start applying it to the sums. Okay. Now, a is a positive integer means I can apply the fundamental theorem of arithmetic and represent it as the product of primes. So I am representing A as P1 into P2 into P3 up to Pn. I don't know how many prime factors are there because I don't know the value of A. Okay. Now, what happens to A square? It becomes P1 into P1 into P2 into P2 up to Pn into Pn. Correct? These are the same factor, and so on and so forth. P divides A square means what? P has to be one of the factors involved in the prime factorization of A square. Correct? So, P has to be, because P is a prime number, P has to be equal to either P1 or P2 or P3 up to Pn. Okay? Which means that P is also involved in the prime factorization of A, which means P divides A. Okay, I will repeat once again. A is a positive integer. I can apply the fundamental theorem of arithmetic and represent it uniquely as a product of primes. So, then I figure out the prime factorization of A square as this. This is basically P1 square into P2 square up to Pn square. Correct? P is a prime number. It is a random prime number. I am saying that P is dividing A square, which means that since P is a prime number and is dividing A square, it has to come in the prime factorization of A square, which means that one of these terms has to be equal to P. Now, let me ask you, can P be equal to P1 square? It cannot be equal. The reason being P is a prime number. P1 square stops being a prime number. Suppose P1 is equal to 3. What happens to P1 square? It becomes 9. So my P cannot be equal to 9. It can only be equal to a prime number. So my prime number P has to be one of the values P1 or P2 or P3 up to any value Pn. Now since my P is one of these values, it appears in the prime factorization of A as well. So, if a random prime number P is dividing A square, it has to automatically divide A also. I hope it is clear for you. Let us take one example and see how this theorem can be applied. Let us say we have a number 6. Now, or let us start with A square 36. So, my value of A will be 6. Okay. Now, how can I represent my 36 as, how can I represent the prime factorization of 36? So, 36 I can represent as 3 square into 2 square, which is 9 into 4 basically. So, if I say that 2, a random prime number, divides 36, I can say 2 divides 6 also, which is the value of A. Clear? So, please understand that we are not talking about any factor. We are talking about prime factors over here. Now, let us see how we can apply this theorem to show that root 2 or root 3 or any number is irrational. Okay, so now let us start with the first and the basic one. Remaining all the proofs are, more or less, not more or less, or I think almost exactly the same as this particular proof. So, study one properly, you will get the rest of them. So, the first one is prove that root 2 is irrational. Now, this particular proof we are doing by means of contradiction. So, by means of contradiction means we will say that this is true and we finally prove that it is false. So, there are different ways in which you can prove a theorem. So, sometimes we prove certain things using induction. So, mathematical induction is a concept that you will study next year in 11th standard, and we have our normal proof also. So, let us do this by means of contradiction. So, by means of contradiction means we need to prove root 2 is irrational. So, we are contradicting it by saying root 2 is rational, and we finally get to a point wherein we have to accept that root 2 is not rational. So, it has to be rational. So, let us see how we can write this. Root 2 is rational means I can represent root 2 as in the form of P by Q. So let us say I am writing root 2 as a by b, where a and b are integers and b is not equal to 0. Now let us assume that root 2 is a number like 6. So I can represent it as 18 by 3, or I can represent it as 36 by 6. Anyway, any which way I can represent, but you can see that there are common factors over here. Correct? So in order to bring it down to the lowest form, which is actually 6 by 1, we cancel out the common factors. So suppose you are representing root 2 as a by b, and we are probably we are thinking that a and b has got common factors. Let me cancel out the common factors, and after cancelling out the common factors, we write it as p by q, where p and q has no other common factor other than 1. Clear? And q is obviously not equal to 0. Okay, so I can write root 2 into q is equal to p, cross multiplication. Now I can square both the sides. So what would I get? 2 into q square is equal to p square. Clear? If 2 into q square is equal to p square, 2 and q square are the factors of p square, which means that 2 can divide p square, or p square is divisible by 2. Or I can also say that, taking into account just the previous theorem that we just learned, I can say that 2 can divide p also. 2 is a prime number, right? So 2 can divide p as well. 2 can divide p. So I can represent p in terms of q in terms of 2 also, which means that 2 can divide p basically means p is divisible by 2. Okay. I can write p is equal to 2 into x. P square is equal to 4x square. Okay. So in this particular equation, I can write 2q square is equal to 4x square. What do I get after cancelling out? I will get q square is equal to 2x square. Okay. Now what do we understand from this? 2 can divide q square, which means 2 can divide q as well. Correct? So 2 can divide p and 2 can divide q means 2 is a common factor of p and q, which goes against our earlier assumption that p and q do not have any common factor other than 1. So since our assumption has proved to be wrong, I have to say that root 2 is irrational. We will go again through this. We need to prove root 2 is an irrational number. In order to do that, we assume root 2 is rational. That is, by way of contradiction, we are going to prove this. Because root 2 is rational, I can represent root 2 in the form of p by q. I am writing it as a by b, where a and b are integers and they have some factor, they may have some factor in common. If they have any factor in common, check them out, bring it down to the lowest form. I am writing it as p by q. So p and q do not have any factors other than 1 in common, and q is not equal to 0. So far, it's a basic definition of rational number. Okay. Because root 2 can be written in the form of p by q, I can cross multiply. I will get root 2 into q is equal to p. Now I have an equation. I am free to add or subtract the same term. I can square. So I am squaring both the sides. So I will get 2 into q square is equal to p square. What do I understand from this? 2 and q square are multiplied together to form p square, which means that I can divide p square by 2 without any problem. So 2 can divide p square. Our previous theorem states that if p can divide a square, p can divide a also. So if 2 as a prime number can divide p square, 2 can divide p also. Okay. Suddenly we find that p is divisible by 2. Since p is divisible by 2, I can represent p as 2 into some number. If I say that 36 is divisible by 2, 36 I can represent 2 into some number. This number is equal to 18. Likewise. So p is equal to 2x. I can square again. P square is equal to 4x square. So I am getting the value of p square as 4x square, which will substitute in this first equation. So I will get 2q square is equal to 4x square. 2 and 2 get cancelled. I will get q square is equal to 2x square. Oh my god, what am I saying now? Q square is the product of two numbers, 2 and x square, which means that q square can easily divide 2. So not q square can divide 2, q square is divisible by 2, my bad. So I can say that 2 can divide q square. Our theorem, 2 is a prime number, so it can divide q also. So I find that 2 is a number that can divide p as well as q. But here we already assumed p and q has got nothing in common. That is where we started. So our assumption was wrong. Root 2 has to be an irrational number. Clear? Prove that root 5 is irrational. You know root 5 is irrational because 5 is a prime number. It is under the square root. It is irrational. We start with root 5 is rational. Our assumption, we are going by contradiction. So root 5 is represented in the form of a by b, where b is not equal to 0. So we are removing the common factors if there are any from a and b. We get root 5 is equal to p by q. Now p and q do not have any common factors other than 1. Cross multiply root 5 into q is equal to p squaring. So from this we understand 5 and q square are factors of p square. So 5 can divide p square. So 5 can divide p by our theorem. Therefore, I can represent p is equal to 5 into x, because if I can divide p, which means that p is a multiple of 5. So p is equal to 5 into x. We do not know the value of x. We are squaring, we get p square is 25x square. I am substituting the value of p square in our first equation. I will get this. Cancel out the common factors. I will get q square is equal to 5x square. So 5 and x square are factors of q square. So I can say that 5 divides q square, which means 5 can divide q also. So suddenly we find that 5 can divide p and 5 can divide q, which means that p and q has a common factor of 5, which goes against our original assumption that p and q does not have any factor other than 1 in common. Therefore, root 5 is irrational. Right? Prove that 5 minus root 3 is irrational. Now, this is a combination of a rational number 5 and an irrational number root 3. Actually, this is even more easier than the previous one because we already start this sum with the knowledge that root 3 is irrational. We don't need to prove that root 3 is irrational. We already, accept the knowledge and use it over here that root 3 is irrational. Again, we start with contradiction by saying 5 minus root 3 is rational. So, 5 minus root 3 can be represented in the form of a by b, where a and b are integers and b is not equal to 0. Now removing the common factors, we are going to represent 5 minus root 3 as p by q, where p and q are integers and q is not equal to 0 and p and q are coprime, which means they do not have any common factors other than 1. Now, I am taking all the rational part to one side. So I get 5 minus p by q is equal to root 3. Now, what can I say about the LHS? I can say that this is a rational number. Since p and q are integers, p by q is a rational number. The difference of two rational numbers is a rational number. But on the RHS, I have got root 3, which is an irrational number. A rational number cannot be equal to an irrational number. Therefore, our assumption that this is rational is wrong. 5 minus root 3 is irrational. So I hope this is clear to you. If you want me to explain again. So 5 minus root 3, we assume it is rational. So I can represent it like this. Removing the common factors, I represent it like this, where p and q are coprimes and q is not equal to 0, p and q are integers, etc. etc. Now I am taking all the rational numbers to one side and the irrational number root 3 to the other side. I know this is a rational number. This whole thing will be a rational number because 5 is rational and p by q is rational. A rational number cannot be equal to an irrational number. Therefore, this is irrational. Now suppose instead of 5 minus root 3, you have got 5 minus 2 root 3. Same way you will be doing. So you will be doing that 5 minus 2 root 3 is a rational number. 5 minus 2 root 3 is equal to a by b. 5 minus 2 root 3 is equal to p by q. You will get 5 minus p by q is equal to 2 root 3. Again, take 2 to the denominator over here. You will get 5 minus p by q divided by 2 is equal to root 3. All these are rational numbers. So, a rational number cannot be equal to an irrational number. So, you don't have to worry about the combination that you are having over here. Just segregate the rational number to one side and say that it cannot be equal to an irrational number. We need to prove 7 root 3 is irrational. We assume 7 root 3 is rational. It is equal to a by b. Now, removing the common factors, this is equal to p by q, where q is not equal to 0. P and q are coprime. Same thing. Now, segregate the irrational number root 3 to one side and p by 7q to the other side. So, I can say that this is a rational thing. This is an irrational number. Both cannot be equated. Therefore, 7 root 3 is an irrational number. So, same logic. Though the combination of numbers that they give you might be different, apply the same logic and do. But if they are asking you to prove the basic, root 3 is irrational or root 2 is irrational, apply the theorem and properly write the complete proof. See guys, we have covered almost all the basic type of sums which are mentioned in the NCERT textbook. I was looking through some reference book, R.D. Sharma right now. So I saw that there are a few sums which are slightly more complicated than the ones given in NCERT. Now we never know what comes in the board examination. So let us try out a few of those sums. Suppose you have a combination of numbers root 2 plus root 5, root 3 minus root 7, anything for that matter, and they are asking you to prove it is irrational. Our basic logic will not work. We are assuming this is equal to a by b, then we cancel out the common factors and then write p by q. See here, there is nothing to segregate because it is already segregated. Left side is irrational, right side is rational. We are assuming this is rational. That is our original statement right now for the time being. Now what do? See, we had to put a basic irrational number on one side and complete rational numbers on the other side. That was our task. So now let us see what we can do with this. I am going to take root of 5 to the other side. Okay. So now I will be squaring both the sides, because I have got a root 2 over here and a root 5 over here. So I need to eliminate at least one term. So I am going to square both the sides. So I will get 2 is p by q minus root 5 the whole square. This is of the form a minus b the whole square. So when you open it, you will get a square plus b square root 5 the whole square minus 2a into b. Okay. Now this is p square by q square plus 5 minus. Okay. This is what you are getting. Now, I am going to segregate the rational terms on one side, the completely rational terms on one side. So, p square by q square is a rational term, plus 5 is a rational term. This is a term containing a root 5. So, I will keep it on one side. So, 2p into root of 5 divided by q is equal to p square by q square plus 5 minus 2. I have taken the 2 to this side. So, here I will be getting p square by q square plus 3. Okay. Now, if I am taking the LCM over here, this becomes p square plus 3q square divided by q square. On the LHS, I am having 2p into root of 5 divided by q. Now, I am going to take the only rational term which is root 5 and keep it on one side. So, I will get root of 5 is equal to p square plus 3q square by q square into q divided by 2p, cancelling out the common terms. So you can see now that root 5 being an irrational term is on the LHS. All the terms which are rational is there on the RHS. I cannot equate a rational term to an irrational number. So I have to take it that my initial assumption where I started from root 2 plus root 5 is rational was completely wrong. It has to be an irrational number. Okay. Here you can see that I have proved root p is irrational where p is a prime number. It's a basic. So if p is a prime number, prove that root of p is irrational, like saying root of 2 is irrational. Here I am taking any random number. The proof is the same, except that here there are no numbers to play with. Everything is variables. So I am assuming root of p is equal to a by b. Cancelling out the common factors, I am writing it as x by y. I cannot write it as p by q because I have already used p over here. So x by y. So cross multiply, square. So I can say that p divides x square. So p divides x. Our theorem. Because p divides x, I can write x as, which means that x is a multiple of p. So p into z. I am squaring it and I am substituting it in the equation 1. P into y square is equal to p square into z square. I am cancelling out p. I will get y square is equal to p into z square. So what can I say? P and z square are the factors of y square. P divides y square. So according to our theorem, p divides y also. P divides both y as well as x. Therefore, our initial assumption that x and y are coprime does not hold. Therefore, if p is a prime number, root of p has to be irrational. Okay guys, we are done with the first chapter, real numbers, HCF, LCM, all those things, fundamental theorem of arithmetic, and now we are also done with irrational numbers. The remaining part of the chapter has been deleted for you guys, which is terminating and non-terminating, recurring decimal part, decimals. So if you are interested in that, please go through it, because it is not a very interesting topic. It is an okay interesting topic, but still, somewhere when you are writing some examination, you might need it, you never know. So again, I am telling you, any doubts in this particular chapter, so you can mail me in the mail ID given below in the description box.